We're going to start the new lecture, chapter 8. So let me bring up, I posted a few material online already. So we're going to do introduction of the material first. And then if we get extra time, we will be able to do some give me a second. I hope you all get the chance to watch the video, but even if you haven't, you still have the time to post questions and comments by Wednesday. And I talked to Professor DeLeu. He is willing to answer if you have any specific questions for him. So I should say any question that I don't know how to answer, I will just refer it to him. So feel free to post anything you want. And so for today, sorry, this is taking a while. So for today, I will introduce hierarchical modeling in the way that usually like a statistician will learn about it. But of course, as you can see in the particular introduction video that he did, there are so many different variations. And for him, I think if you watched it, you realize it's actually talking about two types of hierarchy. So he talks about the group level model and then the individual level model in his video. So you will notice that it's not just a hierarchy between the group and the individual. So it's actually separated for each of the style that he did. It's going to be a hierarchical model over there. So hierarchy, of course, we say like when you talk about hierarchical modeling, we naturally think about models, say, especially data, say like students within schools, which will be the example that we're going to use from the textbook. And then patients within hospitals, members within households. Like the last part is actually what I did for my PhD dissertation. So you see that a lot of times data group naturally, just the way that they arise. So hierarchical model is really trying to avoid doing the analysis separately for each group, but somehow we like to say the word like borrowing information, trying to like get across the board to use data from other groups to make better inference about the group that you're doing. So pretty much you can think of if the group outcomes are kind of similar, then it probably makes some sense to try to estimate when we have across the board some kind of link across all of the groups. Okay, so this is the general idea. So you can think of if the groups are similar, then there should be some useful information in the other groups when we're trying to make inference about the particular group that we're working on. So hierarchical model is, I think, a principled way to how to make that happen. Okay, so in frequentist methods, there are hierarchical model as well. So if you have taken some kind of frequentist course before, you probably know about this ANOVA, analysis of variance. So ANOVA is trying to do within group variance and between group variance and compare them. So this is actually related to what we talked about from the diagnostics, because last time we talked about the Gell-Mann-Rubin diagnostics, remember? You run multiple chains for your Gibbs sampler or for your MCMC, and then trying to check if things are converged well enough. And then over there, the idea is similar to ANOVA. You look at within chain difference or variability and between chain variability, and you compare them. Okay, so for ANOVA, like the analysis of variance over here, a pretty standard approach will be, so you notice that the textbook talks about example of the US math scores. Okay, they have student scores nested in schools. And then a natural way for ANOVA to be done will be, okay, now I have so many different schools. I think they have 100 schools. And then each school gonna have a different number of students, but each student gonna have a score. So ANOVA will be able to ask the question, say, oh, what if I want to know if for all of the different schools, the mean of the score will be the same or not? Okay, so that's what like the ANOVA will be doing. And it's called ANOVA analysis of variance because it's trying to get like a grand mean of all of the students and then a group mean from each of the group, and then trying to come up with sensible and also following certain distribution type of analysis over there. Okay? So I did include some material at the end of the lecture slides. I just don't want to spend time talk about it, but you will see that like if you go through the slides at the end, there are 2 pages about ANOVA, how ANOVA can be done for this context. But for us, we're gonna focus on hierarchical models in a Bayesian way. So sometimes you might have heard other terms like multi-level models. So that's the same pretty much. People use that interchangeably. So based on the other name, multi-level, you realize that in the data set or how the data came up, it's going to be multi-level type of stuff. So for example, students within schools, it's multi-level because you have individual students, but also you're going to have students nested in the schools. And then, so you have these 2 levels over there. And we're trying to make sense of this hierarchy and then to borrow information across different schools. Okay, so usually you're going to use a Gibbs sampler to fit the model if the full conditionals are obtainable. So this is the foundation. I mean, you need to be able to derive the full conditionals in order to use a Gibbs sampler, right? So the textbook, the example that they do is again under the normal assumption, like everything is the normal model, et cetera, et cetera. So they actually didn't talk about how you derive the normal, derive the full conditional, but you can kind of read off the answers based on what we learned before. So that's what we're gonna do a little bit today as well. But starting from this chapter, I'm bringing into a new, I would say a new, like something new that you'll be able to implement those models using a package for you. So far what we have been doing, like Gibbs sampler, like you're doing homework, et cetera, you notice that you will have to code it up yourself. You have to derive all of the full conditionals and then code it in a principal way, which is definitely good practice. But starting from this chapter, I will still show you like the code that I posted on Moodle is still the Gibbs sampler. Like I changed it from the textbook and put it in the form and in the notations that I'm using in the slides. But the other set of the code that I posted is called JAGS. That's just another Gibbs sampler, like JAGS. So that's actually our package. People have been writing and it's been very successful to do MCMC for you. So you will see that. So, I mean, not for today, but on Wednesday when we come back, I think we'll get the chance to compare the code a little bit. So the general code, like the one that we've been doing so far is just like very standard. You have your MCMC, like Gibbs sampler in particular. You initialize the chain, you have this and that, and your Gibbs sampler, you have like full conditionals and you sample one by one and you save them, and then in the end you produce them and use the CODA package to analyze. That's the pretty standard. And for the hierarchical models with the student math scores, you will still be able to do this because later soon you will see that because everything is under the normal model, so you can still derive all of the full conditional. Okay, so this is what we can do based on what we have learned. But for example, what if it's some distribution like in the full conditional that you cannot recognize what it is, right? So another whole area of Bayesian methods, like in terms of computation, is called Metropolis-Hastings algorithm, which is actually what if you don't have your full conditional recognizable, what you can do. So to me, I think it's definitely exciting, but I think based on like the pace as well as like what people want to do based on your feedback, I think we should spend more time looking at examples. So now we're gonna rely on things like JAGS, like the package, to do the sampling for you, even if, say, the full conditionals are not recognizable. Okay, so this is like the general framework, but I still want to like at least cover this one more time in the hierarchical models with the student within school math score, because this case, you can still do full conditional, you can still code up your Gibbs sampler, but the other set of the code that I provided on Moodle is the JAGS code for doing the same model. Okay, so you can see that, yeah, like how things are like coded up in the JAGS language, and then how that can do the Gibbs sampler for you. Okay, it's pretty efficient over there. And actually I found, like I did both, and I don't think I can replicate everything using the JAGS code, so you might be able to help me with it a little bit as well. Like I provided, you'll see, like I provided on Moodle, but maybe I missed here and there a little bit. Maybe there's some like mistake in the code. So feel free to comment, but I just want to give a heads up that for this chapter, we're still gonna do one Gibbs sampler, okay? But then You also see how JAX can do the Gibbs sampler for you, so you don't even need to derive all of the full conditionals. Like life is so easy from now on in that sense. But that you can think of this as like giving you the freedom to explore the different models. Say like now, because I don't have to worry about deriving the full conditionals, I can put any kind of prior. I can try any kind of things, right? So you are given the freedom with JAX, but it doesn't mean that things get easier. Because once you move to that realm, you will have to think about what kind of priors I want to do, what's the implication, et cetera, et cetera. So just be prepared and think more creatively. And I think once we cover the JAX code, say for the hierarchical model, you might realize now because of the package JAX, you'll be able to do a lot of different kinds of analysis that you want to do. So you might have some new ideas about your project as well. Okay, because now based on what we have done so far, you realize, oh, I need to know the full conditionals if I want to do some kind of MCMC, right? So this is a limitation, obviously, but JAX will be able to give you the freedom, so you might start thinking about different things that you want to do. But anyway, so this is just a quick intro, and let's look at the particular example first. And on Wednesday, I will bring the example that Professor DeLayu developed to our class as well. But to be honest, I don't know exactly like how everything is done over there. So like, I think some of you make a post, say, asking how to, like, I do have the JAX code over there, but I don't understand completely what they are. And the data set is not in a tidy form as of right now. So for now, especially today, to introduce the hierarchical idea, we're gonna still focus on this math score, which is actually the same in the textbook, so you will be able to refer back. But I would like walk slowly as how the hierarchy is developed, and then how, in this case, the Gibbs sampler can be derived. Okay. All right. So the math score example, it was collected in 2002. Okay. So it's student score from the 10th grade, and they sampled 100 large public schools, and they got 1,993 students in total. So you see that not every school is gonna have the same number of students, okay? So in fact, if you look at the data, which is actually uploaded on Moodle, within each school, a random sample of students is selected, and the number of students range from 4 to 32, okay? I mean, like we don't know much more detail about how the data collected, but we should assume that it was a random sample of students from each school, and the size range a lot. Okay. All right, so a hierarchical model for this data. So let me just maybe like talk a little bit about why there's some hierarchy over here. So earlier, we were saying that you have students nested in schools. So you might have some like school effect, you can think in that way, and then individual effect, in fact. Okay, so here, if you think about each school, we use J as the index, and then you have J from 1 to capital J. So here, because you have 100 different schools, so capital J is 100, and we use N subscript J, which is the number of students in the Jth school. Okay, so based on what we know, capital J is 100, and NJ is between 4 and 32, okay, based on what we know. Okay, so this is the first part. And then if you go into each school, you will realize, okay, we're actually going to assume, because it's math scores and people believe that it might follow a normal distribution, so people are actually going to use the normal distribution to model it. So the idea is, for each school, you're going to have a school-specific mean, which is mu j. Okay, let me actually start writing on this. Yeah, so the mu j over here is the school-wide average score. Okay, and then you're also gonna have, because we're gonna use the normal to model it, so you need the mean and variance. So we have sigma j squared to be the school-specific variance of individual test scores. Okay, so now notation, pay attention. We use Yij to denote the ith student in the jth school. Okay, so J is the index for school. Okay, and I within the school J will be the index for the student. Okay, so if you think about the index here, J is from 1 to capital J. That's fine because you have 100 different schools, and the I goes from 1 to NJ because NJ is the total number of students in that school. Okay, so multiple things over here. So the normal model that people are usually going to put on is this. So mu ij, because it's the ith student in the J school, is going to be a normal distribution with the school-specific mean and the school-specific variance. Okay? So this is what we're going to say at the first level. At the first level, it's looking at each individual data point. And in this case, in the context, is the jth school, the ith person, going to be follow a normal distribution within each school. Okay. All right, so this is one part of the hierarchy, and then you also notice that you can return some summary, because now you're pretty much breaking students. I mean, they're naturally nesting schools anyway, but you can return summary statistics like y bar j to be the sample average in school J, and Sj squared to be the sample variance in school J. Right? So you put people into different schools. They are in different schools already, so I'm just assuming. So in like a NOVA class, I think people would like to have, say, like things like this, and this is like school 2, school 3, and then school J, which is 100, for example, over here. Okay, so we're just saying that each of the y, so here will be yi1, there's yi2, because that the second I is the observation in the school, and the second j, which is the school indicator, right? So over here, that's how the notation is going to work. So pretty much, I'm just saying that for any school, j equals to j. Okay? So yij going to follow its own mean and variance being a normal distribution. So this is just saying that you were looking at the, you can think of it at the micro level in the sense that I'm only looking at observations within one school, and I will have a particular normal distribution for each observation in the same school. So if you try to expand it, you're going to have 100 different terms like this, right? Because you have one normal for each school, so you have 100 normals for all of the schools. So this is at the first level. Okay, this is how the model is set up at the first level. So how about the second? And the second is the part, I mean, where we actually gonna start thinking about building this hierarchy. So let me ask you a couple of questions first. So this is what we just thought about earlier, okay? So this is what we did. Yij is normal with mu j and sigma j squared. So natural question is how are we gonna put a prior on mu j? Okay. Say now, like, let's just focus on the mean for now. Don't worry about the variance. Let's just like go easy with the one parameter normal, like what we did before. Suppose sigma j is fixed, or we are not doing analysis about it. If I just gonna focus on the mean, should we put a normal? And if you agree, what kind of normal that you would like to put? Now we're just like treating each group separately. Each one is a normal. Yeah.
So are we assuming in this case, I guess this is the question that makes it hierarchical, or are we assuming all mu j are pulled from some single prior distribution?
Mm-hmm. Good point. So I think Eli is one step ahead, that you're already thinking about how to build the hierarchy. So, but say here, if I'm not thinking about it at all, if I'm just looking at all of the schools separately, I'm making inference about schools separately. Naturally, I would just put a normal over there, right? Like what we did before, because it's conjugate. All of the analysis will be straightforward to come through, okay? So what normal, like that part of the question would just be like, say like mu 0 and tau 0 squared, and then all of the stuff that we have done before, okay? But the second part, which Eli actually responded more to, is how to introduce the idea that maybe all of the mu j's are related. So the idea here is that, okay, because mu j is the school-specific mean, okay? And I assume, or someone would believe that maybe all of the means are related in some way, okay? i.e., the average score of each school is related to each other. So how can we introduce a way to set up the model that you'll be able to like introduce this particular idea? So I think Eli just mentioned, if you believe that all of the mu j's are related to each other, you might just assume that they all come from one particular normal distribution. Okay, so that's actually what we're gonna do. So the backup. So I still want to go through here a little bit more in more detail, because it's not just saying that, oh, because I believe they're related, so you can put in this way. So first of all, because you were just taking, I mean, you have 100 different schools, but the 100 different schools, after all, still just a random sample of all of the possible schools in the US, right? So first of all, it makes sense to consider the schools, the 100 schools, just as a random sample from all possible schools. So if now you think that the grand truth, the real truth out there for all of the schools in the US, if you believe that the mean is mu and tau squared is the all school average scores, then it will make sense that, oh, now, because my 100 schools is just a random sample, so the mean and variance, which is mu j and sigma j squared, say in mu j in this case, I can assume that because it's a random sample and it's coming from the grand truth of all of the schools in the US, then I can think of mu j coming from a particular normal distribution with the same mean, like I shouldn't say the same mean, with mean mu, which is the overall mean of all schools, and tau squared is the variance of all schools. Okay, so you can think of, so I think this is a key idea, introduce the hierarchy over here, and I think it's still some backup, like understanding over there. It's not because I believe they're all related, so I'm just gonna put in this way, but it's more about, you can think of the school, 100 schools that you have, it's just another random sample. You just have one more layer over there, okay? And then if you believe that mu, so this is the notation here, if you believe that mu is the overall mean of all possible schools, like that's the population, and then tau squared is the variance of all schools, then you can assume that, oh, each mean is actually just coming from the same normal distribution with the grand mean of the truth, and I mean the grand variance of the truth as well. Okay, so this is the way that you introduce the second level of the model. Okay, so think about this. At the first level, it is about each observation in each school, like each observation of a student in each school, right? So over there, we put a normal, and it's very school specific. So you have mu j and sigma j squared. And the second layer, or second level, is talking about how I'm gonna believe, or how I'm gonna put a prior, or like even think about how my mu j arises. So here we introduce the second layer, saying that all of the mu j's actually coming from the same normal distribution with some mean mu and some variance tau, which a tau square, which you might guess that we're gonna put prior on. Okay, so these are the two layers over here. And you see that this kind of setup, so far I'm not dealing with sigma j square at the moment. You can, of course, introduce that one extra layer as well, because I can believe that, oh, sigma j, all of the sigma j square are gonna form the same gamma. And then you can introduce one extra stuff over there. But for now, we're just gonna focus on mu j, because it's kind of slightly easier to deal with that. Okay? But you can see that, like hierarchy, if you believe, like if the data arises in the hierarchical sense, a lot of time it makes sense to do the hierarchical model. Okay? And the way to do it is not that much more complicated. It's actually, so this particular example is built up upon what we have done so far with the normal model. Okay? All right, so, okay. So this will be the hierarchy over here, the second level that I talked about over here. And this particular hierarchy means, I just want to stress it one more time, the school level means vary about an overall mean mu with variance tau square. Okay? It's just talking about all of the mu j's now at the second level. I'm only looking at all of the mean. Okay, so one key knowledge for all of this to happen is called this idea of exchangeability. I think we talked about this very early on in the introduction introduction lecture. But here, exchangeable, you can just think of as like index doesn't matter. Okay, like all of the IID stuff that we have seen before, you can think of as exchangeable. Say like I have 100, so in this case, I have 100 schools. I mean, even if I change the label, it doesn't matter that much. It's just, I know it's 100 different schools, but in terms of notation, I believe that all of this, I mean, because it's a random sample, I'm just going to assume you can exchange them in any order that you want. So we're making the assumption that all of the 100 schools are exchangeable. So that's at the school level. And then students within a school are exchangeable. So once you're looking at a particular school, all of the observations are exchangeable. Okay, so this is the key backup in order to do the hierarchical model. All right, so one more thing which I actually like from the textbook is they actually put things in this particular form that can help us. This is analogy to the ANOVA, if you have done ANOVA before. Okay, so this is how you're actually going to break it down into the levels. Say at the first level that we're talking about, it's each observation in the J school going to be IID, a normal. So I just put a P over there just to represent. And that's talking about within group sampling variability, because you're thinking about all NJ observations in one school. Okay, and the model over there is to introduce the variability over there. Because you have a school mean, which is mu J, and you have a bunch of Y1J, Y2J until YNJJ. They follow a normal distribution within each school. So that kind of variability or that kind of model, it's from the within group. Okay? While if you're looking at all of the mu J, which is the mean of each school, so mu1, mu2 until mu capital J, that capital J is the total number of schools, because at the second layer, we'll put it to be another normal, right? So you're looking at the difference. So if you think about this particular distribution over here, because we're talking about this being a normal, and we talked about this hierarchy, what this hierarchy means. It's saying that the school level means vary about mu with variance tau square. So this is talking about, because now we're looking at different mu J. Each mu J is a school specific mean, right? So at this level, it's gonna be between the group. So group here, just gonna be between school, okay? But this is a more general term. Here is the between group sampling variability, because over here, each of them is IID, a particular normal, but there is some variability among them. Okay, so one is within, one is between. And the last part is the prior. Okay? So this will be another way to represent the model, and you can see how like the model is making the assumption of how the data is being analyzed. Okay? And again, I was saying that if you have taken some course related to ANOVA, you probably have seen something like this. And it's not that, I mean, I think it's, you can think of this as an analogy over there. All right, so last point over here, you can actually definitely put more like extra layers, especially about the sigma square over here. Yeah, and all of the priors for those as well. So maybe, maybe I should have theta. Yeah, here it should be theta sigma j squared. Sorry about this, because I'm trying to say that you can put prior for each of them. Okay. But this is not what we're considering for now, because that just adds extra complexity. But you can do it, especially now, like I said, with JAX, like you just one line code, ask JAX to do that layer of the prior, you can do it. Mm-hmm.
So you're saying we're not going to specify the prior distribution.
Sorry, yeah, so I'm saying that we will, so right now, this is what we have. We have this as well. We're gonna put a prior, which is this prior, okay? And right now, so this was a typo. I was trying to type sigma j square. So here, mu is, yeah, it's for this over here. Yeah, we're gonna put, I think, did I put a prior? Yeah, so what I was trying to say that, like, this is the most important in terms of thinking about the hierarchy. Yeah, but because that's how the data is arise, like how we put the data into different layers, but you do put priors and stuff on this later. Yeah. Mm-hmm. Okay. All right, so this is what we have. I just want to summarize. And so at the first level, it's about the observations within the school. So notice here, the title is saying that we're gonna just assume 1 sigma square, okay? We're not like doing multiple sigma j squared just to keep it simple. So you see that it's going to be the common sigma square over here for each of the school, and we're like making inference about it. So this is the first level about the data, and the second level is about the mean. Okay? So we've been talking about this, so hopefully I feel comfortable about this setup. So down here is just like, for those of you who want to go through the slides later, these are just means, but pretty much because we developed the model step by step. So you notice that we have mu to be the overall population mean, tau square is the between group variance, sigma square is the within group variance. And so the setup tells us that we need to have mu j, mu, sigma square, and tau square. We have actually not only 4 parameters over here, because j goes from 1 to 100. So if you run the Gibbs sampler, like I did it, I think you ended up having 103 parameters for this particular model. Okay, so because if you look at it, this is 1, that's the grand mean, right? You have 1 mu, you have 1 sigma square, and you have 1 tau square. But here, this, you can think of this as a vector. You have, because j goes from 1 to capital J, which is 100. So you have 100 different school-specific means that you estimate from the model. Okay, so this is 100, and you have 1 over here, 1 over here, 1 over here. So in the end, you have 103 parameters in total in your model. Okay, so this again is already a simplified version. I said that you can also do sigma j square, right? So if you do sigma j square, what do you have? You can have mu j, sigma j square. You can write it in this, and mu, and then tau square. So you're going to have 1 parameter for mu, 1 parameter for tau square. You have 100 for mu j and 100 for sigma j square. So that means you're going to end up with 202 parameters if you introduce 1 extra flexibilities in your modeling. Okay, so this is just, I mean, a heads up, because later if you try to code it yourself, you should keep track of how many parameters you're estimating. And the general rule of thumb is you should try to reduce the number of parameters, because you're going to be doing some overfitting with your model with the data. But this is a large data set, so you'll see that it's not that bad. But still, it's good to keep in mind. And say, so for the class as well as the code that I share, it's going to be looking at this shared sigma square. Okay, so this will be the analysis that we're going to see. But of course, you can go back to figure out, oh, what if I introduce this sigma j square? Will my inference become better? Because now I introduce more parameters. Like, does my data or my model have a hard time to fit? Or does introducing more variables, or sorry, more parameters can actually improve my inference? So those will be open-ended questions if you want to explore. All right, so, okay, so the remaining unknowns. So first of all, so now you have all of the mu j, mu, sigma square, and tau square. You have 103 parameters. And so for the mu j, because it's already given, I put it in this way, right? So you already have a distribution ready for that. But you should still put prior distribution for the remaining mu, sigma square, and tau square. So that's what Serenity was asking, I think. So here you're going to have multiple. So here you're going to have 3 distributions for them, and that will become the joint. All right, so this will be the part that I was not able, and I don't think I will ever be able to use some software to graph those nice graphs, but I do want to try to do a graphical representation of the hierarchical model that we just talked about. Okay, so this again will be slightly different from what you've seen in the video. So in Professor DeLeu's, like what they do with the cognitive science, like they have different ways of representing models, which I actually like, because you will see, like I have some screenshots from it right after this. But for us, we have kind of like more simplified version of that style, but can still like introduce the general idea. But they will be able to introduce more information. So let me show you what we, the one that we have done so far. So because it's trying to do the hierarchical, so we can try to write maybe I would just do. So this represent all of the data. Okay, I put it in the middle. And this is for school 1, school 2, school 99, and school 100. Okay, so think about, so let me, okay, write it out over here. So our assumption in the model, the hierarchy is introduced in this way. So each observation, so observation I in school J, gonna follow a normal mu J and sigma square, right? That's what we did, okay? And at the lower level, we assume that each mean comes from the same normal distribution, okay? So if you try, okay, so here in the model, I just write, so this, you can, all of this are vectors, okay? It's not just one observation, it's vectors. So think about this, how this is helping us. So we know that mu ij is a normal given mu j and sigma square, right? So first of all, because we assume they're all normal, you will have the contribution. So you notice, this is just one way that we do this. You notice that this is gonna come from different mu j's. Oh, sorry, mu 2. So this is saying that because each school would believe there is a school-specific mean. So at this level, so this is the data level in the middle. And just when I, like the way that I draw it, just on top of that, and you have the arrow, like the arrow over there, saying that it's mu j contributing to yj. Okay, so mu 1 contributing to y1 because that's the mean. Yeah.
2 quick questions. First of all, when you say y1 to y100, each one of those y's is representing the entire data set from that school.
Yeah, so this is a vector. Yeah.
Okay. So we're using the same mu to generate the whole data set from each school.
Yeah. Okay. That's what this is, right?
Right.
Yeah.
And my other question is, we are doing in the end trying to do inference on like the total mean mu, right? Okay.
Yeah, yeah.
So the mu j's are just intermediate.
Yeah, good point. So, right, so from, I don't want to bring it back because I started drawing this, but from the previous slide, we saw that the parameters that we're gonna make inference about, like in this particular model, is mu, which is the grand mean, sigma square, tau square, and then all of the mu j, right? So I was saying that you have 103 parameters from this model. So ultimately, you're making inference about all of them. Yeah. Mm-hmm.
Okay.
Mm-hmm. All right. Okay. So, all right. So yeah. So all of these are vectors. Good catch. Yeah. So I just use like simpler notation over here. So y1, y2. Okay. So okay. So this is, I mean, this is still like the first level, right? We introduced the first level in this way. And if you think about the other half of the first level, will be about the variance, because you also have the variance component over here. Okay? So the way that this kind of representation is doing is usually, I think, put the data model in the middle, and then you fit in, say, in the representation of what are the parameters that are actually affecting or like contributing to my data model. So in this case, because my yij is normal mu j and sigma square, so for each of the y, I'm gonna have a separate mu that's in the middle chunk. But then down here, because I assume it's the shared sigma square, so they're all just coming from one sigma square over here. Make sense? Yeah. So this is, all of this is the first level. The second level is not that hard to introduce in the graph. So what people usually do, because they all come from the same normal, right? Like what we have seen over here. So you're just gonna bring it back on the top to do mu and tau square. Okay. Yeah, so this will be the second level. Does that make sense? Like just the way? For me, I think it's intuitive. I guess it's so intuitive to me until I saw the other ways that they're doing. I think it's even better. But it's hard. I will show you like right after this. Because the drawback of this representation is you only just have the arrows. you know like what are like being contributing to. Say here, it's both mu j and sigma squared to contribute to a particular yj, because that's how the data is set up. And then on the top, it's gonna be mu and tau squared down here. But if you have watched the video, and the next slide I will show, you'll see that in that area of application, they're actually gonna have even extra like distributions out there for you to show what exactly is the prior or whatever it is over there. I think in that sense is more intuitive, because for us, this is just saying, oh, it's both mu and tau squared to determine all of the mu j, and then it's mu j and sigma squared together determining the yj. Okay? You only see the relationships, but you don't see exactly how those distributions are being specified. Okay? But overall, I still think, to me, maybe because I was trained in this way, I still think this is intuitive enough. And the textbook has the same representation on in that chapter. So if you want, you can go over there. But again, I realized the textbook was using theta for all of the means again, so just don't get confused. Okay, they're using theta for all of the mean, while here I prefer using mu, because I think it's easier to keep track of things. So you will see that the code that I shared on Moodle was using mu everywhere, while the text, like the sample code they use, is about theta. Okay, but it's the same thing. It's just about the group mean, the school means. Okay. So the graphical representation makes sense? So a lot of times, I mean, you can imagine this way. If you're given a particular data set, and even if you're just trying to figure out what kind of model that I can use, even if it's not hierarchical modeling, you can still try to do a graphical representation this way. It's just for it's just for hierarchical modeling, I think it's particularly more straightforward if you do this. So you can get it clear, what are your hierarchies and what are things contributing to others. Okay, cool. All right, so let me show you what they do, which I find very intuitive. Yeah, it's Halloween, so yeah. Yeah. Okay, so this is like, if you watch the video, you realize this is one of the models that they, Professor Deloitte did. So this is just for one particular power function. So you see that they have 3 parameters. They have alpha, beta, and gamma, okay? And then the outcome is the response time. So you can write response time over here, and depend on time t. Okay? So the way that they represent the model, which I find intuitive, especially for people with, I think, not very strong math and probability or stats background, will be, oh, because now I'm putting like here, because they're using a normal to model it, right? So they just put like a proxy of the normal down here to show you that, oh, this is the distribution they're using. Okay? While for like alpha, and I think later, yeah, they use both gamma distribution for the alpha and gamma parameters, and then use a beta for that beta. So to me, and then of course the sigma over here, which I find surprising that they're using a gamma for sigma, which I was just a little bit surprised, because I think usually it's gonna be gamma for the precision, right? Yeah, so maybe there's some particular reason why they do that in their application. But again, they're using JAX, so they don't have to code it up themselves. So I think that does give you the flexibility. But just a heads up, because to us, what we have done mostly, remember, is sigma square gonna be a gamma, sorry, inverse gamma. So 1 over sigma square will be a gamma. That's what we usually do, okay? But they do it differently, which I still don't know the detail that much, but okay, so this is like one particular model that they represent. And Professor DeLeo did mention that they have 9 different models. It's 9 different lines that they're modeling. So I think the next stuff that he did is something like this. But obviously, so yeah, so I think he only get the arrows for the beta, because I mean, in theory, you should get all of the arrows here. I don't even want to do it. You have to get this gamma for all of the like alpha here and here. So you're gonna have, so here you're gonna have 9 arrows. So in theory, you should have 27, because you have 3 sets over there. But again, this is a good representation, I think, of the hierarchy over here, because you can see. So what they claim, as far as I understood it, will be for all different words. If you have watched it, I still recommend, I mean, you should watch it because you should post some comments on Moodle to get participation grade. But if you have watched it already, you realize that they're having 3 different types of letters, right? And then 3 different types of learning style. So what they claim is that the response time, each of the response time going to be 3, like each response time is its own power function, right? But then the hierarchy is introduced saying that even though all of the like outcome say it's its own particular power function, but the experiments or researchers believe that all of the parameters, they're related somehow, right? So here you have 9 different curves, 9 different like power functions being like introduced over here, but they assume all of the beta parameter. I think that's in the learning theory, which I don't understand, but it's just in the theory that they believe in this particular power function, all of the beta, they should come from the exact same distribution, okay? So that's why they have this beta together and then giving the direction of the arrows to tell you, oh, that's exactly the same distribution that I'm using, okay? So you see the hierarchy over here. At the observation level, you have a bunch of response times for different letters, okay? But then of course, all of them, I think like it is a power function for some reason because of the learning theory as well. But again, because the power function is gonna have 3 different parameters for each of them, but because certain theory back up the idea that you should put the same distribution for each of the 3 different parameters over here. So that's why you see that this beta is for all of the 9 betas over here, right? And this gamma is for all of the 9 alphas, and this gamma is for all of the 9 gammas. Okay, so that's the hierarchy. So in this particular model, if you count how many parameters there, it's gonna be, how many parameters here? Just gonna be alpha, beta, and gamma, right? If they're gonna assume that they all come from the same. Is that right? I think so, maybe I'm wrong, but based on this particular representation, I think that's gonna be how many parameters that you're gonna have. But of course, each of this is different data set, so they're like estimating it all together. But this particular hierarchy that they are doing, I think it's 3 parameters. But again, this is the first model that he presented, and he said that this is limited, remember? Because this is only like the group level. Yeah, and later he extended to the individual level. And of course, over there, you're gonna have many more parameters over there, okay? But again, I kind of like this kind of representation. I mean, yeah, so in that field, they have a textbook called Doing Data Analysis, and they have all kinds of representations in this way, which I find nice, because the one that we usually do, say from the stats background, will be more like the one that I showed you before. Yeah, not telling you like the distribution of them, you just know what contributes to what. Okay, but still, you can still do it. Okay, all right, so these are, again, a little bit tedious, but you do need to put priors on all of the other 3 parameters. So I'm just using what the textbook is doing. So mu is a normal, 1 over sigma squared is gamma, 1 over tau squared is gamma. And then down here, this list is just summarizing what are they, like all of the hyperparameters over here, what are they? And this goes back to what we have done before in the normal model. Okay, so we won't go into detail over here, but pretty much mu is a normal, 1 over sigma squared is a gamma with those parameters that you find familiar with. We put them in this way because it's easier to interpret later. That's what we did before. Okay, so this is not the focus for this particular chapter, but I hope you do find it like familiar from before. Okay. All right, so the textbook didn't talk about how they derive it, so I won't force you to do the derivations either, and it probably doesn't, I mean, you have got enough practice from homework and exercise in class, but I do just want to say it one more time of the general procedure, okay? The general procedure of how things are done. So when you do posterior inference, so here we're gonna do Gibbs sampling, meaning that the full conditionals can be obtained, okay? So how to get the full conditionals? So first of all, you start with the joint of the posterior, Okay? So joint of posterior, this is how you're gonna write it. So don't forget you have all of the different mu j's, and then that grand mean mu, the sigma square and tau square, okay, given the data. So this likelihood, this is the joint prior. Okay. And joint priors, so remember this one, all of them are independent. I show you like normal, inverse gamma, so they just product together. And over here, because each of the mu j is a normal at mean mu and variance tau square, so this will be a product all over here. Okay, and the rest over here, if you try to do gift sampling using the full conditionals, you only collect the terms that involve the parameter of interest that you're working on. Okay, so if you're doing for mu j, like the other priors about sigma squared, tau squared, that can all go away. I only need the prior from mu j. And you notice that all of the other j doesn't matter either. Okay, so over here, I said that you're gonna write a product, right? But if you're only gonna derive mu j, you don't even care about j minus 1 or j plus 1, all of the other terms. It doesn't matter. Like just imagine like how the terms are, like those terms shouldn't matter. So you can jump to this pretty fast, and then this is from the likelihood. Okay, and then if you're doing full conditional for mu, okay, I want the prior from mu, and pretty much, because mu is not in the likelihood. Mu is not in the likelihood. Mu is only in the joint prior that we use for all of the mu j. So you realize, oh, yeah, you don't even need that. And similarly for tau, I need the prior from it, and then also because tau is from the prior of the mu j, because this is the variance of the mu j, so that's going to be what it is. And sigma square is a little bit more involved because it's from its prior, but also, but also from all of the data point that you have to get. That's from, because sigma square is the variance of the data model, right? So that comes into play for all data points. So that's why you have two product over here, okay? One product over all of the observations in one school, and then another product of all of the schools, because each observation matters for sigma square. Okay? Yeah, so again, I'm not saying, yeah, we're not gonna do this. I mean, I'm not asking you to do all of this, but again, this will be a good exercise for you to keep in mind that what matters in terms of deriving the full conditionals. Okay? Only get the terms that it's involving the parameter of interest that you're working, and the rest, because all of this is saying that full conditional is the parameter of interest given everything else, okay? And if you put it behind the conditional sign, that means that I assume I know this, okay? That is given, okay? So the rest doesn't matter. You can think in that way. They're just constant over there. That's why you should only collect the terms that involve the parameter of interest, okay? All right. Okay, so the full conditionals given in the textbook, I'm just listing over here. One key idea, they had a typo, very badly. They had a typo of the full conditional of mu j. So it should be mu. So go back to the textbook and correct it. It should be mu, but they wrote 1 over there. But in their code, it was still right. So this, like the analysis was just right. I think it's just a typo in the text. Okay, it should be mu. Okay, just so you know. And yeah, so I did, I put it on one of the bullet points. It's on page 135, the full conditional. Make sure that it's mu. Don't get it confused. And it's just their typo. But I do want to just talk a little bit about, even though we're not getting into the detail of doing it one by one, I guess nobody wants to do it anyway. But all of this is not surprisingly different from what we have seen before. This is what I want to talk about. Because everything is still under the normal model. Okay, we have learned this before. We have derived all of them. So in here, it's just a little bit more like group them into the right group, et cetera, in order to come up with the full conditional. Okay? Say, I mean, I'm just gonna take one example, maybe this, no, maybe just this mu over here. Remember our old friend of this precision? We talked about the posterior precision will be the prior precision plus the data precision, okay? And that's just the same. It's coming from what we have done before. But of course, there are much more parameters now over here, so everything looks a little bit more complicated, but it's not different from what we've done before. So this is the precision, and that precision, of course, come into down here, because that's what you use to complete the squares, if you still remember doing the complete square exercise over there. And then on top is the weighted average of the prior mean and the sample mean. Right? Yeah.
Maybe I'm just missing this. Where did gamma come from?
Which gamma? Oh, this gamma?
Yeah.
Oh, that's from the prior.
From the prior to
Oh,
now?
maybe I had a typo. Sorry about that. I think. Yeah, what is this gamma? Sorry. It's probably tau. Give me a second. Good catch. So yes, it should be tau. Sorry about that. Okay, so I did catch their typo, but I have more typos here. Sorry about that. I will update this. So all of this, good catch, Eli. All of this are tau. Sorry about it. So this is tau squared, and tau squared. Okay. Yeah, I will correct this after class. But all of the tau, but the rest is fine. So here, so here should still be gamma. I'm sorry. So all of the tau over here, sorry, all of the gamma that I have over here should be tau, but the gamma 0 is right. Gamma 0 is in the prior. Yeah, sorry about that, and thank you for catching it. Yeah, I'll update this, but still, yeah, if it's gonna, yeah, if it is correctly to be tau squared, then this will be the sum of the prior precision and the data precision. While here, this will be the like the precision itself multiplied with the weighted average of the sample mean and the prior mean. Okay, and that's not surprising from what we have seen before. Okay? And then the second normal is pretty much done in the same way. Sorry, here should be tau as well, I guess. Yeah. And then the gamma, we did similar practice before. So I wouldn't go into detail for all of this now, but and again, textbook is not doing it either. They were just saying that, oh, you should be able to read off. So it's just trying to give some context and intuition over here. Okay, but like I said, pretty much since from this particular chapter, we're gonna try to use this package to do most of the computation for us. So you wouldn't worry too much about all of this. But again, if it's give sampler, it's just gonna be from full conditionals, and you will be able to derive. Okay, but of course, like I said earlier, if you cannot recognize the kernel, like you're not recognize the full conditional, we're gonna use a different set of computation mechanism to do it, which we won't, I don't think we'll spend too much, or probably won't spend any time on this in this class, because we can move to using this package to allow us to do more different kinds of modeling. But still keep in mind, I mean, all of like packages are written by people. They're using algorithm behind. It's not something very complicated. So this full conditional, since now we know what it is, we can code it up, right? But then the JAX code, like that particular package can do that for you as well. And it will be a good sanity check to check that if you get the same answers. And for my case, I didn't. So if you guys can figure out what went wrong with my JAX code, that would be good. But I post both of them. And on Wednesday, we're gonna look at them as well. But yeah, so like personally, like my training is mostly in terms of, because, okay, so think about those packages. They claim they can do all kinds of model. But of course, there are going to be some corner that they don't do. And usually that's what a PhD dissertation is about. You try to do more about like complicated model, et cetera, et cetera. Say for my own work, I don't think that can be run on any of the packages out there. You will have to write it up yourself. So I should say, like, because of my own background and training, I don't have extensive experience and knowledge about JAX, but I'm happy to learn, and I think it is very powerful. That can empower us to do different kinds of models. So I guess that can be a justification of why I cannot replicate the results. But feel free to check it out, and I think it will be a good place to start learning. Yeah. All right, so I would fix the typo of all of the gamma over here. So all of this gamma, sorry about this, should be tau. Okay, and once that's fixed, I think this is finally correct. Okay. All right, so okay, so here I introduced it over here, so that will be a good time to, if you brought your laptop. Actually, I should have sent an email about this because I thought we were going to take more time on understanding the model, but since we still have about like 15 minutes, you can actually go to Moodle. I will do it over here as well, so I can sign in and go to Moodle. I posted the data as well as the code over there, so you can actually download it and then try to work through it a little bit. And happy to answer any questions you have. So on Moodle, you will get there are multiple files on Moodle. So for today, I want you to focus on the actual give sampler code, okay, not the JAX. So if you go to the chapter page, chapter part section, you see that we have the slides and then hierarchical model for math score, parentheses R. That you should download that one for today. And also the last one, the math score.csv, that's the data set. Okay, so download this too. And open the R file, work through a little bit. I mean, the sample code in the textbook, they didn't include things like how you're gonna produce all of the plots at the end when they're trying to analyze the MCMC chain. So I provide some of codes over there that you can borrow and learn from. Because one of the homework questions will be very similar to this. So you're gonna use a related idea over here. Okay? So yeah. If you haven't brought your laptop, maybe you can try to see others. And for this one, I think just play with the code and then work through it as much as you can. You should also spend some time after class, hopefully before Wednesday. Because Wednesday when we come back, we will look at how this is done. And then also start learning about this JAX code a little bit. So I will walk through, I can log in Zoom over here and then show my desktop. Okay, should be good now. All right, so I will share my screen of the R code and so the first part, install the package Coda, that's for analyzing the MC, like the give sampler chain later. But also install like a new pack called inverse gamma. It's just later easier for me to plot things. So I introduced those two. And then reading the data, which is the CSV file, read math score. So if you do it, you're gonna see it's 993 observations of two variables. And okay, right. So all of the priors asked from the text. So I introduce this. I can explain a little bit of the code over here. So the starting values over here, As you can see, there are multiple components over here. So first of all, I'm getting how many schools are there. Okay, so that's by doing. So if you let's click the data to have a look at the data really quick. So there are 1,993 rows, and each row has 2 observations. Okay, it's the school index, and it goes from 1 to 100, and the math score of that particular student. Okay, so in order to know how many schools are there, I'm using a function called unique. Okay, I'm uniquing like the first column of the data set and then return the length of it. So that gives me 100. So J is 100. Because if you look at the Y, like all of the schools, so at the beginning is 1, but later it's 2, 3, 4 until like 100. So you'll see that this particular unique and then use the length will be able to tell you how many schools are there. And the next one over here, I'm just like using, because I'm trying to save all of the values later. So I'm just going to initialize it to be a like a vector of length 100, which is J. And then each of them is NA, because later I want to save things into it. So this will be one practice. You can also do like REP, which stands for repetition. You can also do REP0 or REP1, etc., like whatever you prefer. But I think like using NA is probably better than most of the other ones, because you're gonna override values, right? So if by chance, I think it's easier if you have NA, so you can make sure that you like loop did run through, that there's no extra NA over there, okay? So over here, this is just starting, okay? I'm trying to get all of the Y bar, which is the school mean, okay? So it's a loop, J from 1 to capital J. And it's the variance, the Y bar, the variance, and the sample size for each school. So after that loop, I already record all of the Y bar, SV, and N. And lastly, those are the starting values for my mu's. Okay. All right, so once you go to the setup, MCMC, set seed, here I just follow the textbook, I set seed to be 1. And I'm gonna run my chain for 5,000 times. So I have capital S to be 5,000. And then these 2 matrices over here are the matrices I'm gonna use to save my chain, like save my samples later. Okay, so mu J is all of the mu J that we talked about in the lecture. So we're gonna have S number of rows and J number of columns, because you have capital J number of mu J's. Okay, so this is gonna be a 5,000 by 100 matrix. Okay. The last one here is MST. I was actually trying to figure out like what it means in the text. They were using SMT. I guess it actually stands for mu, sigma, and tau. So they just have a new matrix with number of rows to be S. That's the number of rounds that you're doing. And number of columns to be 3, because you have 3 different parameters. Okay, so that's set it up. And later you're going to see that you're going to keep recording, like assigning values into it. So the MCMC algorithm is pretty much over here. So you have a big for loop outside, running through all of iteration. So it's small s, s in 1 to capital S. Okay, so this is the biggest. So starting from line 42, you see that that's the big outer loop over there. Okay, okay, but inside, so first of all, I'm sampling all of the new values of mu J. And that is from the full conditional that I show. I mean, you can actually, if you have your textbook with you, you might want to just open the textbook for that particular page so you know how things are done. So for all of the mu, which is the theta in the textbook, it's on page 135 on the top. I'm just using that formula with 1 replaced by mu. Okay, that's a typo from the textbook. So this loop is looping through all of the different J's. Okay, all right, and then you're gonna sample new values of sigma squared. So line 51 to 57 is using the full conditional from page, also from page 135, but it's in the middle part, like 1 over sigma squared over there. Okay, so I'm trying to figure out, because there are multiple summation over there. So you need to be careful about that. And then lastly, you're gonna sample, or second last, you're gonna sample a new value of mu. So that's from the full conditional on page 134 in the middle. And then the last one is sample a new value of tau squared. That is from the inverse gamma. Okay. And then I'm gonna store my results in here, the last few lines, and then I'm ready to run my MCMC. Okay. So let me run this really quick. And you can try it. I mean, if you download the data in your laptop, you can just run just as fine. It should be the same. Okay. And also, I put this print S over here just to make sure that my MCMC is running. Sometimes, I mean, because this one is not that fast, like 1 second it's done. So earlier I was worried, oh, it was something gets stuck. So this will be a good practice to print the iteration index, so you know that it is running. So here you see that it just like keep going from 1 to 5,000 and I'm gonna stop. Okay. All right, so down here I include, so the rest of the code is pretty much just how to produce the plots that they have in the textbook. So I think it will be useful if you were curious about how to make them work. Say for example, on page 139, they have this box plot that is trying to show you, they're actually trying to show like through iterations. There are 5,000 iterations in total, but they're trying to do box plot of every 500 iterations sequentially and try to show how the chain is changing, okay? So if you go to my code from line 83 to 94, that's how to, like one way that I came up with producing those plots. So if you do it, you will see a side-by-side box plot over here with mu, sigma square, and tau square. And just by eyeballing it, I think it's exactly the same from yeah, I mean, we're using the same seed, so it's not surprising that it's the same number, okay? And the rest of it pretty much is the same, like I showed how to get the leg one autocorrelation, because they produce that, oh, I didn't load my, yeah, they produce it in the text. So I thought just include all of those here will be useful, okay? So I think those are very similar to the answers from the textbook as well. And the effective sample size, that's how you're gonna do all of this. I think they're very similar, and also approximately Monte Carlo standard errors. I'm just following what the textbook is saying. And also like the minimum and the maximum of the effective sample size of all of the different MuJs. I think I got very similar, but the last part, I don't get exactly the same numbers, so which might be something you can help me with. I think the textbook was getting, so it's page 140, right before section 8.4.2, they return the Monte Carlo standard errors ranging between 0.02 to 0.05, but I somehow got 0.06 to 0.08, which I think is the only part that I didn't replicate. So if you can help me figure out, I mean, you should learn from the code anyway, because it's useful, and then also like you're gonna use it for one homework question later anyway, but it would be nice if someone can figure out. So I did put a comment there, you will see. I said different from textbook in the comments. So if you can figure out, just post it on Moodle, I will appreciate it very much. Okay, all right, I think we're gonna call it a day because time is running out. So we're gonna end here today. So pretty much we talked about the hierarchical modeling idea with the particular example and just went through the code really fast, but I think you should go back to do it. And on Wednesday, we're gonna have time for you to work it out in class as well. And on Wednesday, I think the key idea, like key material will be how to use the JAX package that I mentioned. So it's posted, like the code is posted on Moodle. So if you want to check it out now, it will be good as well, okay? All right.